Okay, so sorry for that. Okay, so good evening, everyone. I guess no one else will join, so let's start the class. So, we were continuing with the solution of triangles. I forgot to mention a few of the conditional identities which I thought everyone will be aware of. So, but still, let me mention them. So, the first one is sine 2a plus sine 2b plus sine 2c equals 4 sine a sine b sine c. Is this portrait mode okay, or should I switch to landscape? I think this is better. Okay. And similarly, we have three other forms. Second one was with cos. So -1 -4 cos a cos b cos c. Now with the half angles. This one equals this is 1 plus so these are the four formulas. An easy way to memorize them is when the sum form has 2a as their arguments, then the product form will have the same trigonometric ratio. That's the sine. And similarly for the cos. So the trigonometric ratio remains preserved if the angle is twice, or not the half angle variant. Here in these two, the half angle variants, the ratio gets flipped. Trigonometric ratio gets changed. Oh, sorry. I guess my screen sharing stopped. Just a minute. Okay, so I'm back. Sorry for the technical issue. So, so I will prove one of these. Sorry. So let's prove the first one. So sine 2a plus sine 2b is 2 sine a plus b times cos a minus b plus sine 2c. This is the LHS I mean. So a plus b is pi minus c and sine pi minus c sine c. So sine c cos a minus b plus sine 2c. Taking sine c common, we have 2 cos a minus b plus uh, sorry, forgot to break this one. So this is sine c cos c. Actually, you can take the 2 also out. Now cos c is again cos pi minus a plus b, and cos of pi minus theta is minus cos theta. So this one is cos c plus cos c minus cos t, so that's um, twice sine c plus t by 2 sine a and sine b. So, so that proves the first one. Similarly, the rest 3 can be proved. So, and there are a few. Okay, there's another one. So this is the fifth identity. So tan a plus tan b plus tan c is the product of tan a times tan b times tan c. Um, Here, obviously, the sum of the angles is equal to pi, since we are considering them to be angles of a triangle. So a plus b is pi minus c, that taking tan both sides. So tan of pi minus c sorry. Yeah, so it's negative. Tan of a plus b is tan a plus tan b over 1 minus tan a tan b.
So,
Yeah,
so though it doesn't matter, but shouldn't it be ASTC instead of ASCT?
sorry. I wrote it wrong twice, I guess. So this A stands for all, and this sign. This is sine, and this is tan. This is cos. and that proves our identity. Next, there is also a half angle identity. So that was hmm. So how to prove this one? Okay, so I guess now the screen is visible too. Yeah, so we will use those derived formulas for tan a by 2. So what was one of them? I guess something like square root of s minus, just a minute, s minus b into s minus c by s into s minus a. Cyclic sum of that equals 1 by s times s minus b s minus c s minus a s minus c. s minus a times s minus b. So it's s minus c by s. So similarly, the other terms will be s minus a by s, s minus b by s. So 3s minus 2s, s by s is 1. Yeah, and of course you can invert the terms to get the corresponding uh, identities for cot and sec and cosec. So now the inequalities. The first one will originate from this tan ratio, this tan identity. So applying, take observations. So observations are tan A, tan B, and tan C. From AMGM, we have tan A plus tan B plus tan C by 3 is greater than or equal to cube root of tan A, tan B, tan C. Now since we know the sum is equal to the product, replace it with any one of them. So cubing both sides and cancelling out tan A, tan B, tan C. Assuming it's a triangle, so none of the angles will be 0. So we can cancel out. Twenty-seven, right? So the product or the sum is greater than or equals to 3 root 3. Now from, not from here, okay. So that was one result, one inequality. Another one. So it was also a homework problem. We need to show this is less than or equals to 3 by 2.
Sir, in the above problem, how tan A, tan B, tan C are is 3?
Sorry, tan A, tan B, tan C are?
The expression tan A, tan B, tan C means tan A into tan B into tan C. How is it 3? Is it given?
Uh, why did I write 3? No, I
Okay, it's
did
the
this.
minimum value.
Yeah, that's the minimum value. This is a greater than or equal to sign. I'm using AMGM to find a bound, just a bound. It may not be a reachable one or tight enough, but just a bound. Similarly, here we will use a quadratic formula to find the bound. So So let's merge the first two terms first. So cos of a plus b, cos a plus b by 2 times cos a minus b by 2. Uh, let's leave this for now. Nothing to write. So cos a plus b by 2 is pi by 2 minus c by 2. So this is sine c by 2. So now we can break down cos c in terms of sine c by 2. We don't need to take anything common for now. Okay, so let's assume this expression to be something, suppose b. So now let t equals to sine c by 2. This implies, so 2t cos a minus b by 2 plus 1 minus 2t square equals to p. So 2t square minus 2t cos a minus b by 2 plus p minus 1. So that's a quadratic in t. Since t is sine c by 2, which is a real number, in fact in between minus 1 to 1. So the discriminant is positive greater than or equal to 0. So that means b squared minus 4ac is greater than or equals to 0. So cos square a minus b by 2 is an upper bound for 2p times p minus 1. I guess we don't need strict upper bounds. So like, what is an upper bound for the left hand side? Obviously 1. So and p was our original expression. Okay, so now so try to prove this one. cosec a by 2 plus cosec b by 2 plus cosec c by 2 is greater than or equal to 6, given the angles add up to pi. This is also AMGM inequality, just try to find the observations and apply one. Okay, so uh, anyone tried? So the observations are obviously these three: cosec a by 2, cosec b by 2, and cosec c by 2. From AMGM. So there's cyclic sum by 3, cyclic product. So this is, we have to find a lower bound for this one. We can use this one to find that. So the first formula, the first identity that I proved, yeah. So we can use this one, since this one has the product of sine a by 2's, and product of cosec a by 2's can be written as the reciprocal of product of sine a by 2's. So sum of cyclic sum of the cosines is equal to 1 plus 4 times the cyclic product of sine a by 2. From the previous inequality, we know this is less than or equals to 3 by 2. And yeah, so this is less than or equal to 3 by 2. So 4 times the cyclic product is less than or equal to half. So the cyclic product is less than or equal to 1/8. So that's also an important inequality. From this upper bound, we can find a lower bound for its reciprocal. So the cyclic product of cosec a by 2 is greater than 8. So obviously its cube root is so this thing is greater than or equals to 2. Therefore, okay, let me do one more. Yeah, so show that so this has a upper bound of lower bound of 9. If we try to apply AMG with the half weights, so um, or else I guess we can do something more interesting. So we can apply Cauchy-Schwarz inequality. So from CS inequality, CS has a general form a squared b squared plus e squared times d squared e squared f squared is greater than or equals greater than or equals sorry AD plus BE plus CF whole squared. So take the first vector as tan A, tan B, tan C. The second vector as 1, 1, 1. So norm of the first vector times norm of the second vector is greater than or equals to the square of the dot product. So 3 times their cyclic sum of squares. This thing has a lower bound of 3 by 3 root 3, right? So this thing has a lower bound of 3 root 3. Sorry, what am I writing? So squaring that, we get 27. So the cyclic sum of squares of is 9, as we were required to prove. So enough practice for today. Let's move on to. So this is another identity, actually used for not that much applicable, but still since it's written. So cos a times cos pi by 3 minus a times cos pi by 3 plus a. This equals 1/4 of cos 3a. Similarly, sin a times sin pi third a minus a times sin pi by 3 plus a is 1/4 sin 3a. And lastly, so how to show the first one? We have a formula for cos a minus b times cos a plus b. This equals cos square a minus sin squared a. Sin squared b. And similarly for sin a minus b times sin a plus b, we have sin square uh, sin square a minus sin square b. So using those two, we have the LHS of 1 equals cos a times cos squared pi by 3 minus sine squared a. Cos pi by 3 is half. So okay, since we need only cosine ratios, so this is 1 minus why did I get this square?
So, uh, while starting the proof in the first two lines, the formulas you wrote, are they all right?
Uh, am I wrong somewhere? Please, like, okay, let me check this time. So cosine.
So cos A minus B into cos A plus B comes as cos cos 2A plus cos 2B, right? Into half.
So cos.
So that's what is making me confused.
So what is cos 2a? 2 cos square a minus 1. Cos 2b is 1 minus 1 minus 2 sine squared a. So 2 cancels out, cos square a, and 1 cancels out. And we have a negative positive sign, right? Is it positive? Mm,
So it will be plus 1 minus 2 sine
oh
square b.
yeah, sorry. Yeah.
Yes, sir, got it.
So yeah, this is 3 cos square a minus 4 cos cube a. This equals cos 3. And similarly, we can prove the sine one also. And dividing the first two, we get the third one. Yeah, these can be mostly used for finding the value of u, like sine 10 times sine 30 degree times sine 50 degrees times sine 70 degrees are sometimes useful in MCQs and all. So try finding angles or group of angles with common difference of 60. So this has 60. And what else? Sorry. I have to find angles with common difference of theta, right? So I just have to find angles in AP. So 30, 50, and 70 have a common difference of 20. Or whatever I'm doing. So let A equals to 10. So from the above formula, we have sine 10 degrees, 60 minus 10, 50 degrees, 60 plus 10, 70 degrees. Sine 30 is half. So this thing is 1/4 sine 30. So sine square 30, 1/16. Okay, so that's enough of trigonometry for now. So then we can either continue with calculus or move on to some new topic like probability mm, or complex numbers, I guess. What should I do? Okay, we are actually left with inverse trigonometric functions. Okay, so this is kind of a puzzle problem from, I will not mention the topic. So here you have a chessboard. So this is a 7 by 7 chessboard. It can be of any number, doesn't matter. So now we have a like say suppose a horse. So a knight. How to draw a knight? Doesn't look like a knight.
So you write K only.
Okay, so K. So this is a knight, and it can move to this square, the this square. Yeah, that's all I guess. So had it been sitting here at the center, so knight sitting here at the center would have moved to all the 8 squares. So one, two, three, four, five, six, seven, eight. So those are the legal moves of a knight, as we all know. So now the task is to like given any cell, say suppose this one, given a starting square of the knight, you have to find the expected number of uh, jumps for the knight to return to the same cell. So the question is, given an initial starting square on a 7 by 7 chessboard or grid, find the expected number of moves for the knight to return to the starting cell. So just think about it for a moment. I haven't talked about expectation or anything about probabilities, so I shouldn't pose this problem now, but still. This is a very famous problem of Markov chains, which is a like an application of probability in what is called stochastics, right?
So what the problem says, it's kept on the on a starting square. Then
Then the knight can randomly jump on any of the squares that are legal, and then the like the knight keeps on jumping. You have to find the expected number of jumps after which the knight can be found, the knight first reappears on the starting square. No, there's a similar but pretty unrelated puzzle. So, so suppose you have a rectangle like this, and so these are the two diagonals of the rectangle. The intersection point is E. So the question is, can you draw this figure without retracing the lines and without intersecting or like self-intersecting and without lifting the pen from the paper. So anyone heard this problem before? Similar types of problems are pretty relevant in all the sorts of puzzles like on Brilliant and all those. Like this one, sometimes it has the form of a heart. Like drawing, I'm bad at drawing hearts, so let's see if it changed into polygon. So this has one, two, three, four. Only four intersection points. So this question is the same. So this is another figure which can also be used as a same figure, right? Wait a minute. Someone is calling. Just hold on. Sorry, I left the meeting. Now I rejoined. So one of the ways to argue this one is to consider this as a problem of islands and bridges. So this one, the top one has 5 islands. Island A, Island B, Island C, Island D and island D. So from A, B, C, and D, we have uh, three bridges each. So A to B, A to D, and A to E. So now imagine what does a suppose you can draw this figure without lifting a pen and following all the three conditions. So you have to start somewhere, right, and end somewhere. The starting and ending point, like okay. So the starting and the ending points are unique. So suppose you start outside of this. So like what will uh drawing this figure without lifting the pen is equivalent to tracing the whole figure without lifting the pen, and that is equivalent to like visiting each of the islands without without like ever giving up, and never using a bridge more than once, and of course you can't like jump from one bridge to the other. So that's a trail, right? So we need to find if we need to check if there is a Eulerian like Eulerian trail in this uh, network of bridges and islands. So the key here is to observe the number of islands with odd bridges and the number of islands with even bridges. So all of these are have odd number of bridges connecting them, right? So what happens when you have odd number of bridges? Suppose there is this island with a odd number of bridges, the island X. Uh, if you if you were initially outside the island before using any of the bridges to come into island X, so now you use one of the bridges to come into X, you will have to go outside that island since you have to use every bridge. Suppose you use this bridge to go outside, and then again you have to use bridge 3 sometime after that to come again inside the bridge. So anything that starts, if a trail starts outside of that island with an odd number of bridges, then the trail has to end in somewhere inside it. Or if a trail starts somewhere inside a bridge, inside an island with odd number of bridges, it has to end somewhere outside of it. So now we can use this theorem to like say suppose we start somewhere outside of A. A is a odd island. So from this theorem we know that the trail has to end inside A. Okay, so now we found the ending point of our trail, that is somewhere inside A. So if we start from here, we have to like go everywhere, all the bridges, and somehow end inside A. So now let us use a similar argument for D2, since that also is an odd island. So since we said we are starting here at A, so that's also outside of B, and by the theorem, the ending point also has to be inside B. But the ending point is already inside A, so B can't also be the ending point. So that's a contradiction. So the starting point can't be here. It has to be, if we say if it is inside B, then see we are not getting a contradiction since we are starting with B and we are ending at A. So A is outside of B. So no contradiction here. And We also don't have contradiction in A since it started somewhere outside A and ended in A, right? Yeah. But now we have a contradiction here with C since it's starting outside of C and not ending in C. Right. So that's a contradiction. So somehow we are getting a contradiction. There are many similar ways of arguing things, but all of them involve observing odd and even islands. And as far as this one, so let's talk about probability for some time. This one was actually a problem of graph theory. If I should I discuss graph theory? Okay, just graph theory, a little bit of introduction. So graph theory, this is under discrete maths. So what is a graph? So a graph can be of two types, not actually two types. So graphs can be directed and undirected. So graphs are made up of vertices and edges connecting them, right? So if these edges have arrowheads, like these are one-way paths, then this is called directed. And if uh, they don't have arrows, then it's undirected. Oh, simple. So directed graph, undirected graphs. But they can't be mixed, right? Some are directed and some are undirected. Either it's directed or it's not, or it's undirected. Then each of them can be of two types: weighted and not unweighted. Similarly, weighted and unweighted. So each of these edges can be thought of as some links with some weights, any natural number or real number, depends on the problem or situation at hand. They can be also negative. Okay, so formally we define a graph as a ordered pair of the set of all edges in the graph and the set of all, actually the vertices come first, so ordered pair VE. This is the set of this is an ordered set, or it doesn't matter. Now this is a set of edges of pairs of vertices. So any edge that connects a node u1 to u2, sorry, vertex v1 to v2, this edge is represented by the pair of vertices v1 v2. Now the problem is, if this graph is undirected, then v1 and v2 and v2 and v1 represent the same edge, right? So if the graph is undirected, v1 v2 equals to v2 v1, but if it's uh, directed, then it's not. Okay, so V is a set of all vertices V1, V2, V3, and E is set of all pairs of vertices or edges Vi, Vj. So their collection is the graph, right? Now we have something called complete graph. Oh, and before that we have a degrees. So before that we have degree of vertex. So the number of edges coming out of any given node or any given vertex. Let's only concern ourselves with undirected graphs. So then the edges don't have any direction. So the degree of Vi equals to number of edges coming out of it. So suppose the cardinality of V is n. So there are n number of vertices in a graph, and the cardinality of edge is m. So there are m edges. If Okay, so what is a connected graph? I haven't discussed it. So what is the number of uh, yeah, what is the number of maximum number of edges possible in a graph with n vertices? We are assuming no loops and like so assuming no loops. That is, if this is a vertex, then this is a loop edge with both the vertices same. So we are not allowing such loops. So now each vertex has n minus 1 options, or just think like this. What is an edge? Edge is an unordered pairs. We are in undirected graph, so edge is an unordered pair of two vertices. So how many ways are there to choose two vertices? NC2 ways. And you don't need to shuffle them since they are unordered. So m is less than or equal to this number, NC2. Okay, now what is a complete graph? So if E is equal to V cross V, that is the Cartesian product of V without like without AA, such that A is in V. So these are the loops that we are removing from the Cartesian product. Removing the loops, if the edges, if the edges are counted twice, that's not a problem for us. Like they are the same since we are in undirected graphs. So then the graph is called a complete graph. So if all possible edges are there in a graph, then it's called incomplete, where n is the number of vertices. So now, obviously, if in a complete graph, what is the relationship between E and N? So in an edge, every vertex is counted exactly twice, right? So N must be equal to, sorry. So like in a squared or a rectangle, number of edges are 1, 2, 3, 4, 5, 6, and there are 4 vertices. So of course the number of vertices is less than twice number of edges, since uh, if like if the graph was a spanning tree, then the number of edges would have been equal to the number of uh, sorry, so m equals to n minus 1 if this was a tree. So what is a tree? A tree is a connected graph without any cycles. So what is a connected graph? Connected graph. So if there is a path between any two, direct or indirect, any two vertices vi and vj's in v. So for all vi vj in v, if there exists vi vj inside e, then g is called connected. And then we can easily show that in a connected graph, the number of edges are exactly sorry, not in a connected graph. Okay, like even a complete graph is a connected graph. So what is a acyclic graph? Okay, it would be easier for me to explain acyclic graph if I first explain bipartite graph. So a graph is called bipartite if a graph is called bipartite if the vertices can be partitioned into two mutually exclusive and sorry, mutually exhaustive and disjoint sets. So if the set of vertices V can be partitioned into two mutually exhaustive and disjoint sets. So suppose if there exist U and W subsets of V such that U intersection W is null set and U union W is equal to V. This is U and this is union. So yeah, then no and if like every edge is in between U and W. So and if there does not exist, sorry, if for all U1 UI UJ UI UJ in U and WI WJ in W, um, UI UJ, this pair does not exist in the set of all edges E. Similarly, WI WJ also doesn't exist in the set of edges E. This has to be true for all vertices in UI UJ in U and W. Okay. Then G equal to VE is called bipartite. So typically we draw a bipartite graph as two rows of vertices and then connecting a mesh of edges between them. Typically they draw all the edges, but that's not necessary. Even if none of the edges were connected, that too was a bipartite graph. So a quick question. This graph, this square, sorry, this rectangle, is it bipartite? What do you think? Anyone? Anyone wants to answer? Okay, so there are only four vertices here in this graph with also four edges. So now if we put V1 and V3 in one set and V4 and V2 in the other set, call these edges this is 1, this is 2, sorry, this is 4, so this is 2 and this is 3. Right. So all the edges uh, are between the sets. V1, capital V1 and, oh sorry, I used U and W, right? So capital U and capital W. So these are the two partitions of the set of vertices V. So yes, this is bipartite. So next we have connected done, bipartite done. Yeah. So tree. What is a tree? Trees are mostly represented like these. Uh, so this here, sometimes called the root, but that's not unique. Like anything can be root here. So whatever the main criteria for a tree is, it has to be connected. And only if it is connected and it is acyclic. So what is a cyclic graph? Like this rectangle. This rectangle was cyclic. So what makes a graph cyclic? So assume like a bipartite graph is never cyclic. Oh, just a minute. Sorry. Yeah, a bipartite. This graph is cyclic and it is also bipartite. So no, no, not that, but mm, so how to define cyclicity? So like you can only say like if it's possible to, if there exists a node such that starting from edge E1 we can reach the same node, the same same vertex V1 without retracing any of the edges, then the graph is said to be cyclic. And an acyclic graph is a graph which is not cyclic. So now try to show that the number of edges in a cyclic graph, in a tree, sorry, not a cyclic graph, in a tree is equal to the number of vertices minus 1, or m equals to n minus 1. So like see here we have 1, yeah, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 edges and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 vertices. Oh, sorry. I messed up. Wait. So cardinality of E here is 13. Cardinality of V is 14. So this one holds. So to prove it, we first construct a graph like this. Like we take any random vertex v1 and connect any other random vertex v2. Then from that v2, oh sorry, we don't even need to go to v2. Now, sorry, okay, what happened? So suppose these are the set of vertices of our graph. So these are the vertices. Pick any one of the edge and draw all possible n minus 1 edges out of it to every other remaining vertex. That makes the graph connected. So now we have the number of edges equal to n minus 1 since there are n minus 1 other vertices to connect to. So now the graph is connected, and to show it's acyclic is is pretty easy. Like every path is now of length uh, at most 2, and the smallest cycle has a length of 3. That's a triangle. So this doesn't have a cycle. Now, next definition is yeah, that of a subgraph. So what is a subgraph? So a subgraph is just so if we have a graph g equals to v comma e. If we pick a subset u of v and a subset let's call it v bar and e bar of e, then that ordered pair, if it satisfies a few conditions, then it will be called g dash equals to a subgraph of g. So what are the conditions? So the conditions are vi vj. So if vi vj are in v bar, then vi vj, this ordered pair, has to be in e bar if and only if vi vj are in e. So this must happen for all vi vj's. Okay, so then g dash is called yeah, g dash is called a subgraph of g. Uh, Now there is a theorem called Mantel's theorem and Turan's theorem, but there was an inequality before that. What was that? So if yeah, so there exists a no, so let G be a undirected graph with at least one edge, then there exists a subgraph H of G such that the minimum degree of all overall edges of all vertices of H is greater than or equals to half of the average degree of the edges of H, greater than or equals to half times the average degree of the vertices of G. Okay, so before I discuss the proof, there is something called a so there is something called a induced subgraph. So what is an induced subgraph? So again we have a graph G with a vertex set and edge set. We take a subset S of V. Let let us define E dash equal to a set of all vertices Vi, Vj such that Vi and Vj are in S and Vi, Vj uh, you can define it like this. So for all Vi, Vj in V, sorry, in S, if Vi, Vj in E, then Vi, Vj in E dash, then G equals to S E dash is an induced subgraph of G. Okay, so like if you have a graph like a graph like this one, then this graph has this graph as a induced subgraph. So you take five of the vertices and also the all and also all possible edges that are in between them. This one, this one, this one, this one, this one, this one. Then what you get is a induced subgraph. If but like this is not an induced subgraph. Yeah, just this one. This is an induced subgraph, but this is not an induced subgraph since all the five edges are taken, but these two edges are missing. These two edges are missing. So induced subgraphs are in some way unique in terms of the set S of vertices that are taken from the parent graph G. Okay. So now coming back to this proof. So what is the average degree of G? So it is the sum of degree of each vertex Vi in G, right? By the number of vertices V. So suppose we have a graph G, and suppose the average number of the average degree of what should I call it, D. So let's call the average degree of G as dg. So that just means there are vertices with degrees greater than dg and ones that are less than dg. Suppose we remove a vertex with degree less than dg. What happens to the average? So suppose, so in this graph, the degrees are 2, 2, 3, and 1. So the average is 4 plus 4 by 4 is 2. So the average is 2. Now this thing has a degree less than 2. We remove this from the graph. So we also have to remove the edge. So now we are left with this triangle. So what's the average now? It's 3 plus 4 by 3. That's slightly more than 2, right? So it's slightly more than 2. So if we keep on removing the edges whose whose degrees, sorry, if we keep on removing all those vertices whose degrees are less than dg, then eventually we will increase the what do you say? Yeah, we will increase the average degree, like the sample average degree of the graph, of the subgraph. Yes, sorry, we are getting a subgraph. So its average degree will keep on increasing since, and and yeah, and we are also decreasing the number of vertices in that graph, right? Okay, so that proves this inequality, that there exists a graph, a subgraph h of g says that the average degree of h is greater than or equals to the average degree of g. Okay, now for this one, so just degree, we have to find a subgraph such that d by 2. So what are we doing? We're trying to find a subgraph or construct a subgraph by destructively, like from removing vertices from G. So we remove a vertex from G if its if its degree is less than or equal to dg, or should I write? So by doing that, we are either increasing the edge. Yeah, so we are monotonically increasing the average degree of the graph g bar. So let dg bar be the average degree of the graph g bar. Now g has a average degree at least d, right? So on an average, every vertex has dg edges. So there are n vertices. So there on an average, so there should be at least dg by 2 edges in the graph G. Okay. So now what are we doing? We are removing the vertices which have. So of course, just a minute, we can't have more edges, more vertices, more than n d by 2 vertices with degrees less than degrees less than dg, right? Just a minute.
Sir, could you please explain? I didn't understand the last thing.
Just a minute. Let me construct the argument. Okay, so what does our algorithm do? We keep on removing vertices vi's till we have all the vertices vi's removed which are less than dg. The average number of vertices, average degree uh, of all vertices in G. Right, right. So in this graph H, the final resulting graph have all its degrees greater than or equal to dg. So that makes the minimum degree. So the minimum degree of H is greater than or equal to dg. So that actually proves this one also. Okay, now for this one, so the average degree of H is greater than that of G, greater than or equal to, and and half times that average. Okay, so so what can be an upper bound for the average degree of H? Yeah, the maximum degree. So what is the maximum possible degree of a no of a vertex in G? N minus one, obviously, right? So so the maximum degree can be n minus one. Like if the graph H is a complete graph, then only it will achieve its maximum degree. But then this n is less than the original graph, right? So this one is less. So the resulting graph H, let it have nh vertices, and we know it has uh, dg bar is the average degree of the vertices in G bar. So we also know it's greater than or equals to dg. So the average number of edges, sorry, the average degree of h is nh times. Actually, I'm sometimes using g dash to represent h and sometimes represent using h. So don't try not to get confused here. So that is the number of that is the average degree. So what is this thing smaller than? This thing is smaller than n, and yeah, smaller than n minus 1. And what can I say about the degree? So we need to show 2k is less than d. Okay, since it's already past 10:10 almost, so I will discuss the other remaining theorems and proofs next week. Okay, so no assignments for this week. I'm ending the class here. Okay, bye then. See you next week.